Okay, this is the pre-lab video for the Michelson interferometer experiment for Physics 2213. So when you come into the lab, you'll have the following equipment set up for you already. There'll be a laser, a neutral density filter which reduces the intensity of the laser by a factor of 10, and some parts of your interferometer. So you should have by this point read at least the introduction to the lab so you understand what we mean by an interferometer. The interferometer creates two separate beams and then overlaps those two beams to observe the interference. And so the beams are created in the following way. One beam is created from the laser. You'll have to build a beam expander to expand the physical size of the beam so that it's not such a small laser dot, that we create a bigger spot size. Then we enter the interferometer part, which consists of a beam splitter. 50% of the light hitting the beam splitter gets reflected this way towards this mirror, and 50% of the light goes through, straight through the mirror, straight through the beam splitter, sorry. The 50% that hits this mirror comes back, reflects off this mirror, comes back to the beam splitter, and some of it passes straight through onto the screen. The second part of the light that goes through the beam splitter will go through and hit another mirror that you place at this location, reflect off this mirror, back to the beam splitter, and some of that light will reflect off the beam splitter and also hit the screen. So there's two different ways we can hit the screen. One by following this path, and one by following this path. And those two different paths are both from the same coherent light source because they were split off of the same initial laser beam. And so this coherent light can interfere with each other and form an interference pattern on the screen. This is a very sensitive and delicate experiment. You'll notice right away that this is not just a mirror located here. There's this fancy apparatus underneath it. And what that is a linear translation stage. So this is a mount or a stage which can slide in this direction. It can only slide very small amounts in that direction. And so to control that motion, there's a piezo crystal inside this stage which is powered from this power supply. And when a voltage is set to the piezo crystal, the physical size of the crystal changes and it translates into a motion of this stage. And we can get very small motions using this system. The maximum range of motion is only 25 micrometers, and we'll be going about half that. So about 10 micrometers, but we'll be doing that in very many steps. So each individual step is something like tens of nanometers, which is incredible to think about. You'll remember the wavelength of light itself is on the scale of hundreds of nanometers. So we're going much less than one wavelength of the light that we're using in this experiment. Okay, so you may remember that when the light interferes on the screen, you can either get constructive or destructive interference depending on the relative path length of these two paths, of the two different interfering paths. And so what we're going to do is change one of the arms of the interferometer so that we can change the interference pattern from constructive through destructive and constructive again, and so on and so forth. So that's the idea. Technically, setting up the interferometer is quite challenging. You have to be careful and patient and follow carefully the instructions in the lab manual. They're there to help you. I would encourage you, when you're setting up your beam expander, to make sure the beam expander isn't doing any steering of the beam. Meaning, if without the beam expander, the laser hits a spot at the back of the apparatus on the back wall, that when you put in the beam expander, the expanded beam hits that same spot on the back wall. And that requires a bit of patience to get that set up properly. Secondly, I would encourage you to make to make sure everything's happening at 90-degree perpendicular reflections, so that this beam splitter is set up to reflect at 90 degrees, precisely 90 degrees. Thirdly, the experiment is sensitive to motions which are on the order of one wavelength of the light that we're using. So anytime something in the interferometer moves by less than 1,000th of a millimeter, the interference pattern will change. Because we want to study this interference pattern, we don't want things on the table to be shaking any more than, you know, a 10,000th of a millimeter. So, you know, a very, very, very small amount is the amount of vibrations we could put up with. So when you're setting up the interferometer, you'll be adjusting these mirrors, but you should adjust them and then let go and then look at the interference pattern. And then touch them again, turn it a little bit and look for the interference pattern. You shouldn't be holding on to this and expecting to see an interference pattern while you're holding on to it, because undoubtedly your hand is shaking at an amount much bigger than 1 micron, and you'll be sort of just washing out any interference pattern you might hope to see. So when you're actually looking for the interference, just very carefully make very small adjustments, touch it, let go, look and see if you see the interference, and again, so on and so forth. It'll be an iterative process to try and hunt around to find the best way of, or to find the perfect overlap. And it's only the perfect overlap of these two different paths which will give you a nice interference pattern. Okay, so once you find a nice interference pattern, we'll end up putting a photodiode somewhere where the screen is, and we'll run a program that's pre-written for you, a LabVIEW program pre-written for you to scan the piezoelectric translation stage through its through its complete range of motion, while we look at the interference pattern on the photodiode and collect some data using the oscilloscope. And that part is kind of done automatically for you, but what you're going to realize is while you're collecting data, you have to be careful and still, and you can't be tapping on the computer, you can't be tapping on the table, you can't be touching anything on the experiment. Because if you do, you'll invariably shake something in the experiment by more than a micrometer, and you'll just kill your entire signal. So you'll have to be very careful. You'll have to trust that your neighbors, your other students in the class are also very careful, but you're all in the same boat, so you all should just be careful. Avoid bumping into tables or slamming the door to the lab, this sort of thing. That will affect everybody's experiment. Okay, a critical thing you have to remember when setting up the interferometer is that the path length from the beam splitter to this mirror has to be the same as the path length of the beam splitter to the second mirror that you're going to be putting in on the other arm of the interferometer. Or at least they can't be so dissimilar. And so dissimilar is with respect to the coherence length of the laser. And coherence length is a concept that's described in the lab manual. And so as a final experiment, you'll be doing a test to see if you can try and figure out what the coherence length of this diode laser is by actually mismatching the lengths of the arms of the interferometer to see where you stop seeing interference. How mismatched can they be and you still see an interference pattern? And if you get to a point where you don't see an interference pattern, that must mean the coherence length is less than the path length difference that you've introduced between the arms of the interferometer. Okay, that should be it. I want to encourage you again to be careful and precise and patient. Right? This isn't going to be something you set up in 10 minutes, although you're not going to be adding too many optical components. You're going to be struggling for about an hour to get this interferometer set up just right. And so just expect that and plan for that, and don't get frustrated by it, and you should be all right. Good luck.